The last talk will be a funny moment. Unfortunately, the authors couldn't make it to EGSR, so Ilian has volunteered to try to understand and then explain the paper.
That is correct.
So it might be very interactive. You might get better method than we did when we looked at the paper and the presentation. The paper is entitled Precomputed Dynamic Appearance Synthesis and Rendering. The authors are Yaoya Bai, Miloš Hassan, and Iki Yan. And so Ilya Georgiev, probably research, has accepted to present it. We spent some time on the whiteboard. I got some intuitive understanding of what was going on. So if you have some basis on optimal transport, it should work. Otherwise, it's the job of Ian to make it work.
Thank you very much, Tammy, for raising the expectation. I don't know. But okay, so all right, cool. So this should be interesting, right? So this is a paper. Obviously, yes, I'm not an author of this. Due to circumstances, so the authors, they could not attend, but unfortunately they found out that I would attend. So they kindly asked me to present. And so I didn't have much time to look into the work. And last night, while following election results here, I opened my laptop and started looking into this. And I couldn't really, so it seemed like it was, okay, the idea is very interesting, the approach is very interesting. Unfortunately, I couldn't really understand neither from the slides that I was given or the paper, like the core contribution. But it sounded really interesting, so I really wanted to understand it. So I was brainstorming this morning, had a very quick session with Miloš. Okay, just need to check 1 o'clock lunch. Okay, right. So anyway, I was brainstorming, with Miloš, with Tammy on the whiteboard. So I have some decent understanding, and I put some things together. So let's see how it goes. I'll start with the slides. Then when we get to the meat, I'll switch to something else because what's in the slides is not very, at least for me, it wasn't very useful. Cool. So. Right. So first, some teasers for the results. What they want to achieve here is to interpolate appearance in multiple different senses. Right. So here we're interpreting like geometric shapes, on the right side appearance, and this needs to be done on like all these interpolations. They want to do it on the fly. Right. So you're given these 3 base shapes in the corners of the triangles, or the 4 appearances like materials on the square there. And you don't want to pre-compute all these interpolations. It's a continuum, right? But you want to be able to specify some interpolation parameter, and during render time, figure out what this appearance is at a given location based on the interpolation parameter. So this needs to be fast, right? You want to do this during path tracing. So that makes a lot of sense. Right, so I'm going to read some script now. So appearances play a crucial role in computer graphics, including elements such as textures, BRDF, volumes, BRDFs, and which are typically described using distributions. So the technique of appearance synthesis enables the generation of an unlimited variety of new appearances based on a limited set of existing ones, as you remember from the previous slide. However, the appearance synthesis is challenging because we cannot simply blend 2 appearances, or 2 distributions essentially, linearly, without introducing ghosting artifacts, right? So you can imagine like if you just blend between a cow and a duck by just averaging the density, it's not gonna look nice. Instead, we're looking for a natural way to blend or to transition between existing appearances. And due to the complexity of the appearances, blending calculations can be time-consuming and require significant storage space. Right, so if you're just blending the densities, that's trivial, you can do it on the fly, but that doesn't work, so you need something more complex, and that will require computation, so we want to do this fast. Right, so they introduce some framework for precomputed appearance synthesis. Okay, so this framework aims to provide general, efficient, and cross-dimensional natural appearance blending solution. So there's a bunch of kind of goals that they set. They want high-quality natural blending to achieve good intuitive interpolation. They need high performance because path tracing is inherently time-consuming, and you don't want to make it much slower. And also, very importantly, now since path tracing relies on point sampling, it's essential to be able to point sample these interpolated appearances during render time. That will be what that means will become clear in a second. Okay. Okay, right. So this is all based on optimal transport. So we're going to be interpolating appearances using the framework of optimal transport and Wasserstein barycenters. And okay. This is an example, and I'll show a couple more where. All right. So where this is one distribution. This is another distribution, and using optimal transport, the framework essentially moves mass. You can think of it as moving mass from the one distribution to another. The color coding should help you figure out which points here in this distribution end up where in the other distribution. And I'll show a couple more examples in a second. Okay, that's not okay. So now we go to our method. So the core idea here is the core task is to blend between distributions. So as I said, I need to move my. Sorry, I need to switch to Keynote that I just prepared while thankfully, while we're waiting for the. Okay. That's the word? Okay, good. Right. So, so we have two distributions, and we want to blend them. So there are two different, two different ways to blend them. One based on L2, just averaging the values of the functions, which may not lead to a natural result. Imagine if blue is a cow, the orange is a duck. Yeah, you get something stupid. But with this concept of Wasserstein barycenters, which is based on optimal transport, essentially you get this green result. Essentially, you see mass moving, morphing from blue to orange, and this has been done like in many contexts. Like if you want to interpolate between faces, obviously, this is much more natural way to think of this. And again, just now. We can also blend continuously using this Wasserstein concept. So here, on the one extreme, you have the blue distribution. On the right, on the other extreme, you have the red one, and you can blend between. So you can continuously morph between these distributions. So now we're going to the core concept. This is something that I just put together. So you have two distributions. Think of them as each one being one of these Gaussians. But we also represent them with point samples. So we import and sample this distribution, and the density of the points here corresponds to the continuous density. Right. So we have these two discretized distributions, and we want to blend between them. We compute the optimal transport matching, and I'm not going to go into details, but essentially what this gives you is one-to-one matching between pairs of points from the two distributions, so that if you want to morph from one distribution to another, you do the least amount of work, like the least amount of mass is moved. But so I drew this here with these trajectories because this makes it a bit more clear what it means to interpolate between distributions. Essentially, when we have these trajectories, the 0.5 barycenter essentially means we take the vertically the midpoint and we just intersect these lines and we take the points there. And you can also think of like 0.7 barycenter would be here between 1 and 2. It would, yeah. So it's the distribution slowly moves from one to the other. All right. So now here we can have in this work they consider an arbitrary number of distributions. And you can actually, using this framework, this can be generalized to compute barycenters between arbitrarily many distributions, as you showed saw visually before. So now, and the goal really of this work is so during rendering, we actually want to evaluate this distribution, this barycenter, with the interpolation parameter, say 0.7, at some location. We want to evaluate the density here. Now, think of like having one Gaussian associated with each of these points. So we'll be reconstructing some continuous density. So it can be evaluated at any point. So here the right point is where during rendering, we want to evaluate this 0.7 distribution, barycenter. How do we do that? We need to find, in the simplest case, the closest intersecting line, right, between these two. Which line intersects this? So which is the closest line, essentially, intersection. We can have many of these. So with many, the visualization looks more nasty, but even with two, it's not very clear. So back to the distributions, what they do. It's some interesting trick. Tammy enlightened me that it's not a new idea, but what you can do is have a proxy distribution. Let's say we have some uniform distribution now, now the vertical line doesn't mean anything anymore, but I've just used this visualization. So we have these two input distributions, we have this proxy distribution, which is, say, uniform, and we compute the optimal transport matching between each of our distributions, 1, 2, 3 point, whatever, and the proxy, right? So now we have two sets of lines, one-to-one matching. And now, through this matching, we know, I don't have a cursor, but essentially, we know that the second point, if we take the second point in distribution 2, through the proxy, so we know which one it corresponds with the proxy, and through the proxy we can find which point it corresponds to in distribution 1, or any of the other distributions that we have mapped to our proxy. Good, so we do that, and then the next thing we do is construct a hierarchy, a BVH. So we take our proxy, we split it in half in higher dimensions, that will be along the longest dimension. In 1D, it's just the one. So here we split it in half. And now we know which points go in which child node in the proxy. Thanks to the matching, we know which points in each distribution go into each node. So we have this kind of node-to-node matching. And then recursively, we split this proxy, and we have now bounding boxes for each distribution. And as I drew this curved line, right, we know that this node there, the third node, blue node there in the distribution 2, corresponds to that node in distribution 1. I'm getting close to the end of what I was able to achieve during the last previous talk. So let's see how we get. Okay, right. So back to our problem. We want to evaluate the barycenter at the 0.7 barycenter at that location, and we don't know what it is, right? So what we do, basically the idea is, and this is my last slide. The idea is, yes, right, yeah. So the root nodes of the two distributions here, in this case, they overlap. So I'm going to skip them, but let's say, right, we subdivide each of these distributions according to the precomputed hierarchy. Right? So this hierarchy is precomputed, we store it. So now we take the two children in each, And we know that that this left red child corresponds to that other left one. And so we take these bounding boxes and interpolate the boxes themselves. We interpolate these intervals here with 0.7. Just, interpolate. And then we find out in which of the two interpolations our point lies. And then we recurse, essentially, until we find the matching pair. I don't have a slide for that, but yeah, you can imagine. We recurse until we find the two points from two distributions. And then we construct the line between them, and we know where the line is. We evaluate the Gaussian, because we know there's a Gaussian, and we evaluate the density of this barycenter there. So there's no like very solid theory or claims for optimality or anything, but I thought that was neat because you evaluate, with logarithmic complexity, you can evaluate barycenters between distributions that can be arbitrarily many. And dimension also scales with dimension. So that looks pretty neat, and without ever explicitly constructing these barycenters. So I found that neat. I'm not sure how novel that is, but I liked it. So that's why I went through all this effort today to figure out like what is it, and to try to explain it, because I found it interesting. So here now, if we skip the no, that's not what you want to see. But I think we're actually good on time. Sorry. Okay. Okay. All right. Cool. So okay. So. Okay, maybe good. So, right, so you can have your input distributions here, the star, the heart, whatever, and your proxy. So you do the optimal transport between each of them, and this optimal transport matching now allows you to find correspondences between points between any of these two distributions. Now, you were supposed to understand from this slide and this slide and this. I couldn't. Okay. Interestingly, it seems that the choice of proxy here in the red square doesn't matter much. Maybe that makes sense. If you densely sample your distributions, then matchings will be good. So presumably uniform or Gaussian is better. I don't know. We can read the paper and see. Okay. Implementation-wise, right. So they use, after some careful consideration, they found that this geom-loss Python package does a good job for the task. Numerical stuff, I don't think it's important, but that's results. Right. So first, they perform a simple 2D texture blending using this point query and compare results to those of some Justin Solomon's paper. Don't know what that is, unfortunately. Right. The approach is faster, but GPU precomputation seems necessary for their approach, for the proposed one. However, they only worked with 1 million samples. Maybe point samples of each distribution, and simple textures in this situation might not require that many samples. Okay. But right, so this is blending. So again, right, so you're given these 4 distributions in the corner, and you can evaluate the barycenter, like each of the ones in the middle, at any point. Just you can point sample that image without ever computing it in full. Which, you can imagine in a path tracer, if this is the texture, your albedo texture, is exactly what you want. Inspired by a paper by Wojtek Matusik, we extend our framework to blend 2D tileable textures using the point query hierarchical structure. So this is a spiral kind of blending between tileable textures. Another example, now integrated into a renderer, right, to use as a wall albedo. And again, right, this is kind of it only requires some logarithmic time query into a BVH to figure out this albedo. Okay. Okay, this is interesting. Let's see. So this is here we aim to extend the previous 2D tileable texture blending by adopting Berlin noise as the blending weight. So the barycenter parameter, producing seamlessly and infinitely extendable textures. This time we use 2 textures from the Adobe Substance 3D assets, as shown on the right, and apply them as the texture of a mountain. The Berlin noise provides seamlessly and infinitely extendable weights, and the point query structure allows data generation focused on a small range of texture, enabling infinite generation. We're getting, yeah, okay. Ooh. Okay, there's some videos now. Let me show. Yeah. Oh, with time? Oh, good. This is okay, yeah. This was the animation, okay. We would like to emphasize range query by implementing level of detail in our system. In computer graphics, level of detail refers to the technique where the complexity of a model, texture, or other metrics, such as object importance and viewpoint relative speed or position, decreases as the model moves away from the viewer. Right. This is because rendering all the details becomes less critical at greater distances. LOD is widely used in game and animation. So, in our situation, when an appearance moves away from the camera, such as the tree texture in the middle right, each pixel covers larger query areas, allowing the traversal to stop before reaching the leaf nodes. Yeah, I'm embarrassing myself now by showing that I haven't read this line. Okay, another video demonstrating 3D volume blending using point query. Right, so here you're doing volume rendering, and you're evaluating the density, right, at arbitrary locations in space along your arrays, and that density is some barycentric interpolation of 2 other densities. And their framework allows us to point query this barycenter. That is the crux. So all the rest is applications. That's what I found. Very interesting. Yeah, and this is right. This is a 3-way 3D volume interpolation, where the input shapes are at the corners, and then you obtain any of these shapes in between, and you point query the resulting density. This is now a 4-way BRDF blending from the Merle database. Right, so the materials at the 4 corners, they have varying roughness, metallicness, and glossiness values. And the blending weight starts from 1, and that's not very important. It's not clear to me, to be honest, how this is represented as. Right, there are some details about how this barycentric interpolation is applied to color, to other parameters, not just density, right? Because the optimal transport framework works on kind of morphing between densities. But apparently, no, this works on optimal transport, and here there's simple ways to interpolate colors, to just piggyback on this interpolation to do some meaningful color blending. Okay, there's a video of this for blending. Here showing blending like on each row or diagonal. It would have been interesting maybe to see how a naive blending would look. Unfortunately not. So. Cool, conclusions and limitations. So, a novel method that provides general, efficient, and cross-dimensional natural appearance synthesis that can be seamlessly integrated into a traditional rendering pipeline. Again, thanks to this point sampling of various centers. The framework consists of two steps. First one is the precomputation, right, where you calculate the optimal transport matching between each of your appearances and the proxy, and then the hierarchical interpolation. And there are some limitations, as I said, lack of theoretical analysis, why this works is all based on intuition, but any sort of optimality when going through this proxy, there are no claims about that. And that was basically. Thank you very much.